Okay, so now we are getting into the actual day 3 session, and we are going to discuss about the modern SLM upgrades and mixture of experts. I just want to set the stage here for 5 minutes, probably, and then hand it over to Mohit, who is our presenter for today's session. So in the day 1 and day 2, probably you had your introduction to PyTorch, some kind of introduction for the deep learning side of things, and then you get to know about OLM. And in the day 2 that you saw that vanilla GPT-2 architecture, and there were 2 sessions by Vedant and Pranav, and we had a very good deep dive into the transformer architecture there. And now, like what we are going to talk about is that um, the advancements, the architectural advancements happened since GPT-2 architecture. Let me go ahead and share my screen. I'll take over screen share for a moment and then come back to you.
Perfect.
Hope you're able to see my screen, actually. Okay. So there are a lot of architectural advancements happened since GPT-2, and we have GPT-2 model through the trillion parameter MoE systems. And there is one star portal that if you wanted to learn about the architectural advancements happened since GPT-2, I'm sure that some of you are familiar with this author, like Sebastian Raska is a very famous person in the LLM research, and then we follow him very much into this, and he authored a couple of books there, build a large language model from scratch. And there's in the book, if you go into the book section, you will also see that the books that he has authored. And it's kind of a one-stop visual reference. You will be able to find out architecture diagrams, fact sheets, release dates of the models, and then the implementation links. And he has about 96 models that is starting from GPT-2 to the mixture of experts systems, all in one place. And then this will be very helpful for you to focus on what are the architectural advancements. If somebody wants to go back to the architecture and wanted to tweak something in the architecture, transformer architecture, that something would be very helpful. And not just that, it just shows you the evolution, just the endpoints as well, right? So it has given you all the models. You can also go back and choose. Let's say if I'm going inside, so I'm going into the LLM gallery, and you could see all the models available here. And this is the kind of all the models is one snapshot. I mean, this is something like about commercial, but you see that all the models available, what is the architectural advancements happened in this area. And you can also go down and you can see, for example, you wanted to compare between Gemma 3 and Gemma 4, what has happened here, right? That if you wanted to check it out, so you can see the model A and model B, and you can see that what is the attention block that discussed about the difference between model A and model B, the decoder type, KV cache footprint, a lot of these details, like devils in the details, basically, right? So you can see pretty much all the information available here. And so this is a great help that if you wanted to really interested in that area, actually. So it's basically comparison driven, and it's an interactive differentiated tool that you can use it for your advantage, actually. Okay, and again, it bridges the theory and the code, and each card links to from scratch GitHub tutorials, config files, and technical reports, so that you can go from diagram straight to the runnable code. He has the code as well, right? So if you get into this area and then explore this area, you will have a lot of this information available as well, actually. Okay, and so this is what we are going to talk about it, and so you can also find some good SLM friendly examples there. So we can talk about the attention mechanism. If you really wanted interested in checking out what's in it, right? Under the hood, attention mechanism. You can talk. You see the positional encoding, rope versus yarn versus nope, and then all the architectural advancements happen there. About normalization, the decoder type, and then you can talk about the efficiency features like the multi-token prediction, KV cache footprint, sparse attention, etc. And then it also has the per model fact sheets. Like it has, like I said, there are about 96 models, and you could also see that the fact sheets for every model there. So I would say that this is kind of a one-stop solution for you to take a look into it. I can share that link in the chat line, and go ahead and take a look into it. And he also has talks and other things like that, courses and stuff like that. So if you wanted to take a look into it, but this would be very helpful for you to, if somebody is really interested in the architecture side of things. With that, we'll hand it over to Mohit. Over to you, Mohit.
Yeah. Hi, everyone. This is just a second. I'll share my screen. It's visible, right?
Yes, I know some folks have joined actually. I'm sorry that I did not get a chance to admit you because I was just running over with the LLM gallery session. But no, do not worry about it. The actual session is now just starting, and then you can be able to see that the rest of this information in the recording actually. Okay. All right. Over to
Sure.
you.
Yeah. So, hi everyone, this is Mohit, and I am a pre-training researcher at IRO. So, I majorly work in architectural advancements and work related to it. So, today we'll be discussing the modern SLM upgrades and mixture of experts topic. So, the thing is, before we get into it, I'll just give you a brief run through that what you should expect from this session. Um, in last session on day two, you guys majorly saw that GPT-2 architecture, which is a very fairly nascent stage of architecture, which came up from the Vaswani et al. Paper, that is, attention is all you need, right? And he came up with a very groundbreaking architecture of transformer, which we all do use for now as well. But as the time evolves and as the day passes, we have seen that uh, it was not very efficient in many ways, right? And hence, we want some upgrades in the form of in mathematical form or in any different forms. And hence, we went into the rabbit holes of each and every component in the transformer architecture, and we tried to upgrade it through the mathematical advancements, right? And that is the same thing that we'll be discussing today. We will be going deep down into the transformer architecture, pick up the very high values parts and the segments of the transformer architecture, and we'll try to improvise that. So that is what you should expect from this. And this is about me. And if you want to read and get to know me more, you can get on my website mhtjsh.github.io, and let's finally get into it. So we will be majorly looking into these uh, parts, right? Yeah. We'll be first looking at the framing, that what we exactly did in the past days. Then a good form of upgrade in form of normalization. We guys have seen layer norm fairly in each and every part of a transformer architecture. How what were the improvements and how did it evolve from there? Then we'll look into the positional embeddings, that is how we went from learning of positions of embeddings to deriving it on the fly. Then we'll look into the attention cost, that is how we can reduce the compute, that is the amount of flops or is the amount of memory that will be our GPU would be using to give us the same amount of output, right? And then we'll be moving on to feed forward networks, that is the FFN layers, which plays a huge role in the transformer architecture, right? And the last, we will be wrapping up with a very interesting topic, that is mixture of experts, that is how a single layer of how a single architecture of transformer can be divided or else at least we try to empirically do that. That is, we can point out how these specific layers are interested in doing tasks like math, and this specific layers are interested in doing tasks like science, and this specific layers are doing interested in tasks like philosophies, things like that. And that is why we call it as mixture of experts, right? And lastly, if time permits, I would give you a good walkthrough of a node of the notebooks that you'll be doing in. But if not, that's totally fine. The notebooks are pretty well commented and greatly put out for you guys to take a look into, and it would be a brief session. It would be good. Uh, Work for you guys to do in terms of intellect and in terms of easiness that you'll enjoy doing the notebooks. Yeah. So let's get into the mindset that what we'll be looking into today and into today. Yeah. So there were majorly three issues that we used to look into the transformer from the GPT-2 architecture, and which we want to improve, right? So we were majorly not happy with the depth of the architecture that it was looking at. We were not able to generalize our embeddings in the terms of tokens or in the terms of text that was going into the pre-training part. And the third problem, and the major problem, was it was taking up a huge amount of compute, uh, and it was less efficient in terms of hours taking into the pre-training part, right? Hence, uh, the five options that we usually have seen in GPT-2 architecture was layer norm, which we discussed in GPT-2, the absolute positioning of the architecture, the multi-head attention, and then the GLU MLP and dense FFN. This was the vanilla thing, very normative thing. But the upgrades which we got from layer norm was RMS norm, right? It was root mean squared. If we elaborate it while we try to approximate the normalization technique from the definitive steps of normalization, right? So that is what we will be delving into over here. Then the normal positional embeddings which we saw in the GPT-2 architecture was very rudimentary, or else very naive, because we were remembering the position, that is the amount of text that is this is a session. We were almost remembering that session, but we were not able to extract a pattern out of it, and hence we want an upgrade over there, and that is what we called as a rotatory positional embedding. So that was another upgrade. Then there was a multi-head attention, right, which was the pretty non-efficient way to look at the different tokens, and hence we got an upgrade over there. That is what we call as a group query attention. Then we had a GLU MLP, which is an uh, activation layer, but it was not very efficient because it used to take a lot of compute, and hence we got a Swish gated linear unit, and which we call it in a short and sweet term SWIGLU, right? And the last improvement that we had, that we would be discussing, would be dense FFN converting into MoE. That is, the normative feed forward networks are very do possess a high uh, degree of efficiency, but we were not using it that way. So we would leverage that, and we would convert that into different exports. So this would be a major run through of what you should expect from today's session. And before we get into the session, I would like you to give a framework for this, and this is how you should be looking at today's session. uh, we would start from what prior work looks like. Then we would look at what broke, as in what was inefficient, and then what was the fix that researchers got to upgrade that thing which was inefficient, right? So prior work, what broke, and fix. This would be the framework and the whole session, and each and every part would be discussing in the similar manner. So yeah, let's get into the very first discussion. So will majorly look into this two layers of GPT-2 blocks, right, of a transformer architecture. Whenever I refer GPT-2 block, it would be the vanilla transformer architecture, which would be this, right? So maybe you can have a screenshot of it or else a photo of it, and we will be referring it over and over again and again for today's session, as many time as we can. So I would urge you guys to have a visual look around your book or maybe anywhere else in your notes, right? So this is the layer which we will be looking at, that is the multi-head attention and the activation units of the GPT-2 architecture, right? So the positions was fixed, the normalization was inefficient, the attention was inefficient too, and the feed forward network FFN were inefficient too, which we have seen in the Vaswani et al. Paper. And hence, we would be first looking into the prenorm thing, which is the first improvement which would build up for our root mean squared normalization layer, which we discussed in the contents section, right? So when we look into the transformer architecture, each and every layer do have a normalization layer. Because why do we want a normalization layer is pretty simple and straightforward thing. We do not want to deal with random values, right? Nobody like randomness, and so is our architecture today. And that is why we want our values to be in a normalized method or else a manner, right? And hence there was a existing method which researchers or else, the original paper proposed was post normalization, which whenever we are getting the feed forward embeddings, it used to be post normalized, which was not a good way to do, because it used to take differentiation of each and every gradients, and the gradients used to come out with in a bad manner, and it used to end up in zeroth value, which we do not want, right? So that is a basic ground for the prenorm layer. Let's get into the details of it. So yeah, let's discuss what before looks like. That is what post normalization layer, which was the original paper proposed, was this. We used to take the existing embedding, that is XL, and along with the feed forward networks which we were getting, that is sublayers, that is XL, right? So when we want the next embedding, we used to normalize and take the Jacobian normalization. That is, Jacobian is just a fancy way of saying derivative of each and every term, right? So we used to take the Jacobian normalization of both the embeddings, that is norm and the sublayer. But it was not a efficient way. Why? Because we cannot take Jacobian. We cannot keep on continuing taking differentiation of the same value again and again and again, because we have seen that there are many normalization layer across the transformer architecture. So at some point of time, we would encounter values or else embeddings which would be 0.00, or else in worst case scenario, if a negative value, we are getting a negative value, the differentiation of that would not be a good outcome, right? And hence that was the big flaw of post norm architecture. And hence we simply shift the differentiation value into an addition term, right? And that is what we introduce here, a term called as pre-normalization, where we just take the normalization term inside of Jacobian's evaluation outside of it. So we take into the addition term of it. And by doing this, we are not getting the problem of vanishing gradients into our architecture. And by doing that, we would never ever or else significantly reduce the probability of getting the value near to zero or negative. And hence it was a good upgrade, as per the researchers point of view, that we are getting an efficient token evaluation, right? So this is how the figure looks like. Post norm was like we used to take normalization in each and every layer, but we would not be doing that because it was inefficient. As we take a look at the equation as well, we would just take the normalization outside, and before taking the normalization, we would add up all the values in the identity matrix format, and we would take a normalization in just one place, that is after all the thing happen we would take the normalization before that. So that is why we called it as a pre-norm layer, and upgrade over the post-norm thing. So that sets a base for the RMS norm, which we'll be discussing up next. So yes, this is the next thing, that uh, the what is a normalization. We if somebody wants to visualize what normalization looks like, this is a value that is pretty much outside against the mean deviation, which is not a good way to look at things, because if we cannot look at a uniform number across the tokens or else across any distribution, we cannot infer anything as to say from that values. Let me give you an example. If I am saying 10 apples, 11 bananas, 4 grams of chocolate, and 5 grams of sugar, right? Each and every value do have different uh, units, right? And we cannot infer anything from that, and hence we want some layer, some form of normalization layer. And by normalization I would say 10 grams of apple, 10 grams of banana, 10 grams of sugar, 10 grams of chocolate. So this is a normalized way of saying things. That is, we are unifying the units of it, and along with it we are able to deduce some form of standard deviation and the mean out of it, right? So this is what the normal layer norm equation looks like. That is, we used to, this is the existing value, we used to get it near to the mean by subtracting it from mean, and we used to divide it by the standard deviation of it. And by doing that we would normalize a layer, that is which we called as a layer norm uh, block from a transformer architecture, right? But if somebody comes onto my face and puts a gun, that this is taking a lot of compute, and this is taking a lot of uh, uh, inefficient. This is a lot inefficient, right? So if and tells me that you should remove, you should not be getting such accurate values, because uh, we do not care about that much accuracy for now, because each and every token that is in a statement, each and every token would not be that much important, and hence we can remove the mean and standard deviation values with the root mean squared. That is an approximation value of the in the math, right? And hence we call it as a root mean squared norm. And hence from normative layer norm architecture we came up to root mean squared normalization root means square normalization equation. And by from normal layer norm we are now at RMS norm. And it is not that people have totally shift from post norm and layer norm things to RMS norm and pre norm thing, right? Because current Gemma 3 architecture too uses post norm and layer norm as well. But the thing is, what you want from that model would give you a sense of what you should apply into that model. And hence, whenever in the capstone project, whenever you are doing the SLM training from up scratch, you should ask yourself that what you want from your model, and you should apply that. Do you want your model to be very efficient? Do you want your model to be very um, uh, compute efficient or else data efficient? What kind of efficiency do you want from your model, right? So that is what you should ask, and you should apply in such manner. That is, if you want data efficiency, then maybe you do not want so much accuracy, right? And hence you can easily take the freedom to move from layer norm to RMS norm. And a second freedom is compute freedom, right? That is, you do not have so much compute for now in your hand. So maybe the prenorm can be the answer for that. That is, you do not want to compute gradients for each and every values. So maybe just take a simple identity matrix and add it up into the each and every feed forward network, and it would solve the answer for you, right? So that is how you should be deciding that what upgrades do you want to infer it into the capstone project, and any language model training for that matter, small language model or it's large language model for that matter, right? Yeah, that would be the thing about normalization layer for the normalization upgrades for the language model. We would now next be moving on to the embeddings thing. By embeddings, what do I mean by that? Uh, I would give you a statement
So
that
Mohit,
this is
I think now since we are moving into the next section, so
right.
probably we can check the understanding. So, hey, the team, like, how do you feel now? I know that's a great topic. Thanks, Mohit, for covering that. That how did we transition from the post norm to the pre norm, and RMS norm is now kind of a de facto standard, I believe. And
Right.
uh, what do you all like? Any feedback, any comments? You can type it in the chat line, or also like let us know that if you have understood the concept very well. Anything that you want us to cover, touch upon in the RMS norm perspective.
Cool. Yeah,
Yeah.
that would be
Hi,
great.
Mohit. Just regarding the RMS norm, right? The
Right.
denominator part, which is the root mean square of x, right? X, are
Right.
we taking any difference, or the straight away x is going as a RMS? X minus
No,
something? I mean, yeah.
no, yeah, good question. The value which is running over continuously, right? We are not differentiating it from the past values, but we are taking the addition of it, right? This is the root mean squared value, root mean squared Bayes equation. If you can look at my pointer, we are just adding up the running values of it. So this is how it goes. Uh, the We are adding up the running values of it. Along with that, if we have five running values, we would be subtracting, sorry, my bad, we would be dividing it by that, and we would be taking the square root of that whole value. That is what we call it by root mean square. So the x value is just the running value of the gradients, and not the subtraction between the values, because if we are subtracting that value, we are just taking the difference of it, and that would be very inefficient, and it would end up in inaccuracy, a lot of inaccuracies. So yeah, I hope that is clear.
And yeah, as far as ln is concerned, we had an epsilon in case the variance had become zero, right? Divide by zero error is what we are trying to avoid in the layer
Right, right,
normalization. Do we have
right.
such thing over here if x becomes zero? I mean, say for example, divide by zero error be there, right? Yeah.
Right. May x see x actually cannot become zero, because when we are taking RMS norm of x plus one, we have to consider a past value of it. Let's take an example. I would take a freedom to annotate over here. Suppose this is value one, and this is at index value one. This is at index value two, and this is at index value three. Right. So if we want to take uh, RMS norm for this value, because we do not want a normalization for this, because it would give up the same value. But if we want to take normalization layer for this particular term, we already do have number 1 by n over here, right? So it would never give us negative value, because this is first indentation, this is second one, this is third one. So at any point of time, we do have one
There is one over
uh,
in there.
yeah,
Yeah.
one
Yeah.
over there to calculate. And we never
Okay.
take RMS for the very first embedding. Yeah.
Okay. Thank you.
Thank you, Mohit. And yeah, now we can move on to the next session.
Sure. Yeah, thanks, man. So yeah, let's move on to the embeddings part of today's discussion, right? We fairly discussed a lot about normalization. That is, what should we be doing about embeddings? But what exactly is embeddings, and what did what is the inefficiencies in embeddings that we saw in the normal transformer architecture? So embedding is simply the computer understandable number of a statement or else a token, right? Let's take an example. That is, this is a cat, right? So this would be given some amount of matrix number, is would be given some amount of matrix number, or would be given something something, and cat, so on and so forth. This is what we called it as embeddings. So uh, let's take an example. This is a cat. It is furry, right? So furry, and we are just giving these two statements into two-layer transformer or else two-layer decoder, and we are telling it to give us positions of it. That is uh, how it should be learned, right? By that I mean, whenever I'm telling you cat, you should remember furry. That is what we call by relation of a token or as relation of a word, right? And that is what we called as relation of embeddings as well. So what existing thing was happening over here was very naive and very rudimentary way, which we call it as learned embeddings or sinusoidal embeddings. That is, learned is very pretty self-explanatory over here, because whenever we are saying learned embeddings, it pretty much says that if cat and furry is given near in a single line, that means cat and furry is should be near in each and every statement. That is, uh, when it is referring to cat, it should always refer to furry as a statement in any statement, regardless of whether it relates or not. And the second thing is sinusoidal way. That is, we try to give some form of invariance over here by giving sine function into the embedding matrix, and we try to get some amount of um, uh, fanciness over here, but it was not solving it. And hence, and this is the equation of it. I do not want to get into the ugliness of it, because rather than getting into the math of it, the intuition of the rope would take us very far than the math of it, because anyways we're gonna delve into the math, and we're gonna code it out into our notebooks as well, right? So the problem is, it used to be absolute and not relative, as I told you, that it is very learned way and very rudimentary way to look at it. So um, the thing which we use, the upgrade which we got, which is called as rotational positional embeddings, right? So when we let's forget all of the AI and stuff like that. Let's go into our very first standard, maybe probably sixth standard physics of us, sixth standard vector of us, right? A vector to have two components with us. That is the absolute distance and the location of it, as in the point where it is pointing out, right? A times sine theta. That is what we call it as a vector. If we just have a, we call it a scalar value. So scientists came up with something very interesting over here. That is, if we can take something into if we can take the matrix and convert it into a n-dimensional space and point it out into different directions, can we deduce something out of them in terms of relations or not? And this is what we call it as rotations in the query embeddings, right? So this is the simple thing over here, that if my bad, this is the annotation tool, we do not want that. Yeah, let's get into the laser pointer. Yeah, so if this is the key value of our at n is equals to 5, that is the location of it, and this is the query value. We all know the transformer equation, right? KQV thing, query key value thing. Maybe if not, I will just give a brief run through of it. So query value and key. Key and values are always a learned thing in the embedding, and query will always. So there is a query value which would ask for key and value things, and a key and value would reply to the query thing to give out answer that this is what should be appending to the next token. As in, if we are writing this, there is high probability that the next token would be, that is the next key and value would be is, was, or some kind of words in that family, right? So that is what we called as query key value, and just a informal brush up of it, very rudimentary way. Yeah. Let's come back to row. So if our key value at n is equals to 5 position and query value is m is equals to 2 position, it is 3 theta distance between both of them. So by 3 theta, I mean there is way, uh, there are, I mean, you have to quantify each and every value over here, right? And uh, in vectors, we can quantify the value in two terms, by the distance of it and by the angles between each of them. So effectively, what the smart decision that scientists took over here was, we pretty much do not care about the distance of the vectors, that is how long is it, we do not care. We care how far is it. So how can you evaluate how far is it? By the theta angle between the vectors, right? So if you are effectively able to calculate the theta, then we would be able to deduce the distance between each of them, each of the vectors. And if the theta is fairly low between between query and a key, that means that this should be always near to each other. And if we translate it into a very output language, that then the output should be that these two words should be, there is high probability that these two words should be near to each other or next to each other, and hence we call it as a positional embedding, right? Positions of each word should be next to each other or else close to each other, sorry. Yeah. And this is how the intuition of rotation comes into the picture. That is, uh, first people used to learn the positions, people, so they used to just learn all the tokens. But uh, scientists were like, nah, we are not doing that, it is very inefficient way, we'll be remembering the distance between each of them, and by distance they meant angle of the vector, and that is what we call it as rho. So yeah, and this is the math of it. If somebody wanted to take a look, but I'll give a quick run through of it. This is the main equation that we should be interested in. We are taking the dot product between the query and k, and the rm is the notation of the angle between each of them, and we used to take the transpose of the query value, and we take the difference between the angle of the value angle of the value of the query and the key, that is how far is it. If the subtraction is coming to be very low, that means it should be near. If the subtraction is coming to be very high, the transformer would come up and be like, nah, we do not want that, and we multiply it by key value of it. Yeah, that is the math of ROPE. And I would give you a fair disclaimer that I do not want you guys to uh, uh, grasp all of the math for now, because this should be, I would be throwing terms over here in the very um, uh, open terms, right? I'm not closing each and every equation derivation of it, but in my notebook there is fairly good understanding of it, and each and every equations has been derived. So that would be a very good way to look at it. But again, if you guys have any questions over here and anything, that would be very I would be very happy to answer that. So yeah, maybe ROPE was done. If somebody wants to bring up any question, we'll wait for a minute.
So the relative angles between the two vectors remains the same. It's only that both vectors are rotated by same angle. It takes to a different position in the space, hyperspace. Is that what we're talking about?
Sorry, can you please come again?
No, what I mean to say is, in GPT-2 type of architecture, we had not used this rotational angles to the given vectors. That is the query and key pair, let's say. Right. So we
True.
did apply that in the current architecture, let's say Llama 3 type, essentially. So it essentially rotated both the vectors by the same angle. Relative angles between the two vectors remain same, even here as well. So with
Right.
that, like, what is the advantage of Llama 3 over, let's say, GPT-2? I mean, what is the merit of that, like, rotational angle? Yeah.
I'll give you a very good analogy over here. Let's take a student A and student B over here. Student A used to learn a book just a day before the exam, and student B have learned the book probably a week before the exam. So the way and the method that student B would have chosen to learn that book would be fairly different as compared to student A. That is, by that, let me put everything objectively over here. Is um, student B would almost look into the nuances of each and every embeddings and not just mug up all of the things. By mug up, I mean it would not remember the words near to it. That is, this, then the next word should be is. If the probability is very high, the next word should be is always. It's not like that. That is learned way, right? But
Got it. We are randomizing the positions so that, like, it's not prefixated to the data it is learning, but it is the
right,
pattern
right.
that it is learning. Okay,
Right.
thank you.
Why I'll also tell you why it's important, because in large language model the data is pretty huge, but in small language the data is not that big, right? And we do not want a model to remember the data. We want it to abstract the information from it, and hence it would be of very high value to us when we are dealing with small language models. Yeah, that would be another anecdote to that.
Thank you. Thank
Yeah.
you.
Mohit,
So
if you can
let's.
take one more question, I think in the chat line.
Yeah, sure,
The
sure.
first question is, let me take the this related question and then we can go back to the other question. So in rope,
Mhm.
it is just that we are concerned about the relative positions of the two embeddings and not the absolute positions of both vectors. And that makes
Yeah,
the compute easy. Is that a question? That's a question, is that?
it's not about the compute over here. It's about the abstraction of the uh, data. That is, how good are we able to grasp the pattern in the data. It's not about the compute. It's not about saving the GPU RAM, right? It's about the efficiency of the data. That is, how good are we able to extract the pattern with very small amount of data.
All right, it's more than efficiency than that of a compute. Okay, cool.
Yes.
Okay, you can keep on.
Cool. Yeah. So this is fairly. Uh, I mean, this is why. Come again. So we discussed rope, right? And the rope is fairly used in very frontier models as well in today's day and age as well. That is, Llama 2 used 10,000 rope embeddings. Llama 3 used 500 rope embeddings into it, and Gemma 3 also used 10K to 1 million running rope embeddings during pre-training as well. So yeah, that is an example of it. Let's move on to very next thing with which we have with us, and that is the query attention. um, we fairly look at uh, extracting patterns and learning position of each and every token, but we haven't looked at the uh, query attention between each and every layers. That is the self attention layer, right? That is this us in a statement, and there are two ways to look at a statement. We are looking at one query, we are looking at another key, we are looking at one query, we are looking at third key, things like that. That is that which we call it as a multi-head attention. But we also do have to look at ourselves, right? When we say ourselves, we also have to look at the self attention mode of the token. And that is where the positional embedding comes into picture. And people used to give the multi head query attention, that is, used to attend each and every token continuously. And we used to uh, spare a lot of we used to spend a lot of compute over there to look again and again and again at ourselves. That is the self attention of the token, right? So we scientists come up with an good fix over here. That is, they do not want to do that because it's very inefficient. That is, we do not want to remember ourselves again and again. We want newer nuances, and we want to look at we want more ourselves to more depend on other tokens as well. And that is why they come up with grouped query attention. Before that, before we get into grouped query attention, let's look at what the vanilla GPT-2 architecture has to offer to us. That is multi-head attention, that one query would attend to query value 1, query 2 would be attending to query value 2, and so on and so forth, again and again and again, which is a very repetitive process, and we do not want that inefficiency in our picture. And this would be very easier for you guys, each and everyone, to land, because it's fairly self-explanatory. So this is the math and this is the compute efficiency that we are saving over here. That while doing before that, let's get into the picture of it and we'll come back over there. So multi-head used to do each and every token again and again, and it used to attend itself pretty much frequently. We do not want that because it's inefficient. And hence scientists come up with grouped query attention. That is, they used to group the key and value numbers, and they used to just look at the query in for more times, right? That is multiple times. They do not want to look at themselves again and again, because they fairly know that embedding value. We do not want to reduce it again, and hence we come up with grouped query attention. There was another improvement as well, that is multi-query attention, that we look at ourselves only once and we take a look at all the other tokens after that. But it was not a very good method to do so, and hence it's not fairly taken into account. But it's a still there's a paper out there and the people have worked over here on it as well, but the results are not promising as compared to grouped query attention. And this is the compute efficiency of it. That is, we used to take one when in multi-head attention there are 32 kv heads, because we are attending, if we had 32 query values, we are efficiently attending 32 kv heads as well, which would give us 4 GB of compute RAM, which is very high. Why do we want to spend a lot of it? And hence we come up with only mm, 4 kV heads, and we would attend to multiple of it, and this would give us 8 kV heads, and we would be saving drastically on our compute cost. But we do not want to get into the multi-query attention, because surely it is giving us very less compute results, but it's not that of a big uh, uh, fix out there. So no frontier models have adopted this MQA model at all, right? So yeah, this is the math of it. If somebody want to take a look at it, but it's fairly simple. That is, we are just taking the number of weights of the key values, and we are dividing it by the number of group. We just want to get the pretty average of it, or average of each and every key values, and that's the simple math of it. Yeah. That was about GQA. If somebody wanted to uh, have a good question or else anything over here, anything. I mean, the from ROP to RMS norm to GQA, anything. I'd be very happy to answer that.
Sure, we'll give that time for any questions. In the meantime, like Mohit, how much content left, because now we are approaching 1 hour there.
Yeah,
So is it if you want to give them a break for 5 to 10 minutes,
sure,
that's just okay.
sure. I
As a
mean,
presenter, would you like to give 5 minutes or 10 minutes?
sure. I am okay with 10 minutes. I mean,
Wow.
uh,
Okay.
if it's good for all of it. Yeah.
Oh, fantastic. Okay. Uh, As a gracious presenter today. So,
Thank you.
yeah, I think now, before we move on to the section 4, so now it's 9:27, probably 6:57. Sorry, 7:57. I'm not wrong. 6:57. I'm sorry.
Yeah.
And probably we
In the
can meet
meantime,
at
I'll take some questions.
7:07 actually, right? We can meet at 7:07 or 7:08. Okay, so we'll be in break for until 7:08. Please take 10 minutes break and then we'll meet back. Thank you. I'll stop the recording for now. Perfect.
Yeah. So for now, we have discussed majorly three topics, right? We improved normalization layer, we improved positional embeddings, I mean, learning of positional embeddings, and then we improved how we look at ourselves, that is self attention mechanism, right? Next, what we'll be looking at is fairly important and a fairly uh, good improvement, I would say. That is, it was not a scientist would look at and come up trivially, right? It is activation unit improvement, that is swish glue, and we would be taking a look at that, which took over from GELU, which was uh, uh, existingly used activation function at each and every feed forward feed forward network layer, and converted to Swish gated linear unit, right? So yeah, so this is how a normal uh, process looks like. We take an embedding from past layer, then it passes through FFN layer. That is, it multiplies that same matrix by 4 times. That is, if we have 2 by 2 matrix, it would be enlarged into 8 by 8 matrix. By doing that, we are effectively doing self attention. And after that, there used to be activation unit called as GELU, that is to transform that 4 times enlarged matrix. We used to apply GELU equation, which was pretty rudimentary, which we can take a look at over here. That is a normal equation, that which we call it as y is equals to mx plus c, right? Probably not a good way to look at, but in a larger scheme of things, that transformer, what paper proposed, that is transformer architecture, people were in awe of it. So GLU passed by then, but after that, scientists came upon and gave good improvements at GLU layer as well. So yeah, uh, the improved architecture looks something like this. The existing value used to come over here. Then there used to be two gates, right? A gated attention. That is why it is called as gated attention. That is W gate up and W waits up and W gate, and it used to pass through swish activation unit, and then we used to multiply element wise, that is head emit product of it, and then it used to be W down of it, and wait we used to weight down, that is uh, small we used to decrease the uh, enlargement of the embedding, that is ffn, it is getting out of the ffn layer, and then we are getting the output as y. And the equation used something like this. The swish part of it is this, that we used to take a look at the standard deviation of it, and we used to attend only those queries which were highly probable in the standard deviation, and the gated attention would do the uh, uh, Hadamard product, that is the element wise product of it. And this is fairly what we call it as by swish gated linear unit, while GLU was simple y is equals to mx plus c. Over here we used to take the standard deviation of it, multiply it by the element wise product, and then we used to smaller the ffn layer and probably pass on it further, right? So yeah, that's the math which I can show you over here, and this is the equation. We used to take a gated attention through standard deviation, then and by doing that we used to shrink the depth of the four times into eight third of it, that is uh, when an FFN layer starts, the D product converts it into four times of D. That is, the matrix D of 4 by 4 is converted into 16 by 16, which was very inefficient way to look at it. And hence, we applied something called a standard deviation to look at whichever token is coming at higher probability. We would just multiply that, and by doing that and we would just improve that, as in we would just apply a activation unit on those tokens, and by doing that we used to we shrinked 16 by 16 matrix into 8 third of it, that is the equation would come up something be as 16 times 8 third of it, and when ffn ends up it would be again into the 4D matrix of the outcome, right? So that is what improvement looks like. That is, we the memory of the GPU. So this is how GPU architecture works. I am digressing a bit, but I would like you guys to understand why and how it improved. GPU have two components fairly: VRAM of it and the RAM of it. VRAM is where the epochs run. That is, we see 200 epoch, 300 epochs, things like that. Every epoch consume 24 GB, 16 GB virtual RAM, right? But those weights sit somewhere in the GPU as well. That is, the base model has to sit somewhere, right? And the data only moves again and again. So the if we want to put objective words of sitting weights in the GPU, we call it as a RAM. And we want to save RAM as well of a GPU as well of the GPU, right? So by doing that, we are not using four times of the GPU RAM, but we are just using eight third of it. So if we simply do eight third of it, it is coming out to be 2.66 value of it. So effectively, we are just enlarging it to 2.6 times of the matrix in FFN by swish gated linear unit, right? So here we are not directly saving the VRAM of the GPU, but we are saving the RAM of the GPU. That is the static layer of the GPU, right? So that is how this upgrade helps us by not saving the VRAM but saving the RAM. Yeah, that was pretty deep understanding of swish gated linear unit. If somebody wanted to take a deep dive into it, feel free to ask and shoot questions on me. Yeah,
Yes, so I have a question. So may I ask?
hmm, feel free to
So
ask.
yeah, so basically, from the last side, like we have here, this is the like we are typically downing the from 3D to 2D, right? So this is the
No, no,
shrink of, yeah, the shrink of uh, the total evaluation. So we are getting like we are doing the gated thing over here. So why specifically 8D by 3? Like suppose the traditional FFN is using like 4D. So if the current parameter count is approximately something around 2D into 4D, right? So how can you get the output basically? So I think
fair, fair,
uh,
fair. I got a question. I got a question. Um,
hmm,
to answer you, I'll take you to the Gaussian distribution table, right? It's good question. I mean, a friend of mine in the office were discussing that somebody would ask you this, and you are the one. Smart question. So, yeah, when we take a look at the Gaussian distribution, I'll annotate it for you over here, and we'll discuss. Yeah, this is a Gaussian distribution, and these are the layers of it, right? So in uh, GELU, we used to apply GELU to all of the layers, which is not a good way, right? And by this I mean this is the uh, yeah, I'll probably draw it fairly good for now. Yeah, so this is the +1 deviation. My bad. This is the -1, and this is the uh, +1, right? And this would be the -2, and this would be the +3. Let's take it on this side only and not focus on this side. All right. So if you take a look at over here, we are only taking into account the main +1 and +2 standard deviation of the distribution of the tokens, right? So and we are effectively eliminating the plus third standard deviation part of the tokens, and hence by just forgetting the third standard deviation, we are reducing the compute cost over there, right? See,
hmm,
if we are not at all considering this in both the side of the distribution, we are just effectively computing this, right? So I mean, if you are not uh, calculating the thing which you are given, and you are just focusing on smaller thing, then you are anyway going to get smaller matrix, right? And hence
yes. Hmm.
the four times the ffn converted into 2.6 times ffn, right? And that is the math of it basically.
So
We are
yeah,
eliminating
yeah.
this.
So if we eliminate the tokens beyond the two into standard deviation simply to reduce the matrix size, so then like how do you know that those tail tokens are actually redundant basically rather than the real like what like how can we know that what is the like semantically important tokens?
Right. Great question. I'll probably give you intuition first, then math, right? Large
Okay.
language model, Sorrel's language model, is, after all, it's a fancy pattern approximator.
Hmm.
By that I mean, large language model never understand a language, not at all. It just
Hmm.
understands the highest probability or is highly likelihood of the next word. It is good at predicting next things, right? So let's
Hmm.
take an example. You have a track record of coming second in your class for pretty last 6 semesters, right? So there is high likelihood of you coming second again in the seventh semester as well. But
Yes.
uh, right, and the same goes for this standard distribution. And if I want to translate into math over here in this standard deviation, that is, your probability of coming second lies somewhere over here, and your probability of coming first lies somewhere over here, that is less likely, and your probability of failing this stands somewhere over very minuscule in this over here. So that is why I mean, I know that you are not going to fail, and I also know that you are not going to coming the last second thing. So why should I argue with you that you are coming last second, last third, things like that? I know that you are anyway going to be in the first top three of your class. So that is why I am
That means
eliminating my
yeah.
distribution.
So that means we are just we are not actually reducing the compute size. Actually, we are reducing the overall problem size by throwing away the tail tokens. That is the main
Yeah,
fund.
I mean, what do you mean by throwing away? You are not maximizing that. You are not applying that activation unit on that matrix, right? That is what I mean by throwing away. I am not
Hmm.
throwing away that, but I am just not applying and magnifying that matrix.
Hmm. Hmm. Hmm.
Fair?
Yes. Hmm.
We good?
And like one more thing for the the 80 to 40 like conversion thing, like I have so the thing is, if we what can I say, like how can I tell, uh, suppose give me I am giving you the example. So if the, like, suppose there is an optimal width of certain tokens is determined by the some parameter budget, it is already there. Okay, so now, so then theoretically then we should be a predictable relationship between like a like width and the getting capacity, isn't it? Then
No, I
and
didn't. I didn't. Uh, can you come again?
yes, so basically, if the see you are already creating 8D by 3 proportion, that is the hidden width is derived purely by matching the parameter count. It is
Hmm.
very easy to understand. Now, how can we conclude that the performance gain of this, like the GLU which you are using, like is this is the Swiss GLU thing that comes from the gating mechanism rather than simplify from a different parameter allocation. So, what is the fundamental idea from that? Like idea we can get from that.
I mean, I
So.
still didn't fairly get your
So
question,
are
but
you asking
I'll
like why are we getting into this Swiss glue? Why is it is that intuition like because this is an architectural advancement happened that we moved from
Hmm.
like Jello activation to the Swiglu or Swiss glue, the gated linear unit, right? So you can call it either way. But
Yes, that
what
means
is
if suppose we have two models, right? Two models have the same parameter, then same parameter count, but different numbers of projections. Suppose consider this thing. Then why should like parameter count be considered as a fair measure rather than the capacity? So why should I count the
I
parameter
mean,
matching?
things don't. I get your question.
Can you repeat
In
your question
transformer
once?
architecture,
Sorry.
sorry.
I was mentioning to repeat your question once again. I mean,
No, no, Mohit got the question. He can answer.
yeah.
Yeah, I get it. In transformer architecture, things don't change in between, right? You predefine all of it. So in FFN, always the layer magnifies to 4, right? It has to
Mhm.
magnify to 4 times, because see, there's a reason behind that as well. If you want to magnify it 4 times, you are effectively looking at yourself, as in the self attention mechanism sits in the FFN layer. So uh, while magnifying it 4 times, we have to compute something, and to compute something and to abstract and to abstractize and to extract the pattern out of it, we have to apply some form of activation unit, yeah, right? An activation unit, we mean we have many examples and many options to us. There is Tenha, Sigmoid, Relu, etc., but none of it gives us hyperbolic activation, that is pattern out of it. All of them are linear activation unit. But and we there's a reason that why we choose linear activation unit, because it is compute efficient. But
Okay,
switched
then
group is the only linear activation that uh, uh, give, gives us the same output but with less compute. That is
okay,
by
so
less
okay,
magnifying the
understood. But
matrix.
yeah, still I have one.
Prajakta and
Yeah,
Mohit, I'm sorry, I'm kind of a little bit of strict master
Cool.
on trying to
yeah,
control
yeah,
the
sure,
time
sure,
here.
sure,
So let's
Sure.
take the question at the end of the session.
Sure.
So let's
Sure.
sure.
continue the session because in the interest of audience, and we have very limited time. So Prajak, probably you
Yeah.
can also, this is a good discussion to be opened in Discord so that we can continue the discussion and we can also meet in the office hours as well. Thank you very much. Over to you, Mohit.
Cool. Thanks, Pankaj. Let's move ahead. So yeah, we are done with FFN, and let's move on to mixture of experts. So mixture of experts is, again, I gave you a fairly good idea of it, and spoiler alert as well in the start of it. That is, we do not want to waste our compute, uh, waste all of our compute in the model uh, by looking it at the single token, right? That is, we are improvising some in some feed forward. Whenever I'm saying single token, I am always referring to single multi-head self attention mechanism, right? So this used to be, I'll give you an intuition you should take away from this class. It is whenever I'm giving an I'm referring to giving attention to ourselves. That is, I mean self attention. Whenever I'm telling you giving attention to other queries, it's multi-head attention. And whenever we are discussing self attention, we are always looking at feed forward, because as we discussed in the past class, feed forward always looks into the self attention mechanism. Yeah, probably I digressed, but let's continue onto MOE part as well. So yeah, we want to make specified uh, layers of our transformer to be expert in certain topics, or to be expert in certain uh, methods, right? We do not want our whole transformer to learn all of it, and hence we try to come up with something called as expert in the inside of a transformer. Let's get into the uh, math and the understanding of it. So this cat sat on the mat, right? This is a statement, and we have FFN layer. It would multiply the whole matrix into 8D square parameters of it, and by doing that, it would attend each and every token by all of the feed forward networks. That is, all of these feed forward network would fire at the cat sat on the mat. We do not want that. It is very redundant way of doing that. Probably let's improvise that. Yeah. So we would route the we would route the into some FFN cat into some FFN set on some FFN, because there's a reason behind doing that. If we take a look at the on the and the cat sat mat, we are clearly seeing two different abstractions of the words, right? I mean, I do not know the details of the grammars of it, but on majorly refers to grammar, cat sat mat majorly refers to the noun of it. I mean, we know that this is noun, this is grammar, but how do we understand the model? How do we make the machine learn it, right? So yeah, this is how we do it. We try to route each and every token into certain experts, into certain feed forward layers. That is, we take one feed forward network, we break it into multiple chunks. That is, we do not want the feed forward layer as a monolithic block. We would break it into multiple things, and we would let auto-regressively look at each and every token, and the feed forward network would choose by itself that I would be always looking at the grammar. The second feed forward in the same hierarchy looks at the other token and choose that I would be looking at the nouns of it, etc., 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 right? And this is what we fairly mean by feed forward networks and mixture of experts. we are breaking a single monolithic feed forward network into different chunks, and by doing that, we are making each and every feed forward network an expert of a topic or else a subject, right? And this is the math of it, that is, we used to take softmax of the whole uh, pre-training text, and it converts into top k matrix of it, and we just uh, a- allocate allocate those top k values or tokens to only certain experts, right? And this all process is autoregressive. We do not pinpoint this, go and pinpoint the FFN layer that this is how it should go. No, it's all autoregressive, and feed and the architecture have freedom to choose any of it. Yeah, and but by doing this, there is a break, right? There is a loophole that the model can choose. That is, few feed forward networks would be biased and give certain tokens. Suppose expert 2 would always fire in each and every token, or else only expert 2 and expert 3 is learning, and other all FFN is just redundant. I mean, they are not at all passing on to certain weights, right? So here router becomes a very important part in MOE. That is, router makes sure that each and every expert or each and every feed forward network over here is learning something or the other. And how do we do that? How do we formalize this saying? By this auxiliary loss in the trading, right? We just take the multiplication of the number of feed forwards and with the probability of the terms, right? But that is a gated probability thing, and we by doing that we are penalizing each and every feed forward to learn something. I mean, no, none of the FFN should sit redundant, and that is how we make each and every FFN expert of something or the other. Yeah, that fairly sums up for the MOE, and MOE majorly gives us uh, improvement in terms of running memory, right? In during inference time, when we try to infer a model, suppose it's fairly simple task. I'm talking about the Quen models. So Quen and the Kimi K3 models and all of them exploit MOEs a lot. They used to take MOEs and they do something like this. If you have put on reasoning toggle on into the model, they would probably give you the text output in a longer format. And if you put out reasoning toggle off, they would give you text output in a shorter format, but the answer would be same. The output would be same. And how they do it is by making expert, right? And this is where the MOE is used in the Chinese models as well. I mean, uh, now it has been used in many models, but because Chinese models are majorly downloadable and we can explore it, it's a good way to look into the weights of it. So yeah, they use MOE a lot. And yeah, this is where we can see GPT-2 use the same thing, and Llama 3 use GPT-2 use the existing thing, but Llama 3 and Mixtral came up with these same improvements, right? So by these I mean to say, uh, in current frontier models we are seeing these upgrades as well, so they are fairly good and the latest form of research, right? So maybe and it would be of good high leverage use for you guys as well in the SLM training capstone project as well, right? So it can be good tools for in your arsenal. Maybe just the choice is yours, whichever you wanted to choose. And the reason I gave you analogies as well, that why do we use one over the other, right? So yeah, this is a discussion again. As I mentioned, Quen exploits this a lot, but Llama and Gemma models also do this pretty extensively as well. So yeah, that pretty much sums up all the discussion for today. And these are the references if somebody wanted to take extensive read at the papers. And I have given references at each and every slides. If somebody want to take a deeper look at that, feel free to do that, and shoot questions in the Discord as well. I would be very happy to answer that, and I am very much open to questions for now.
So I had a question regarding can I go now or later?
Yeah, just before that, I think Mohit, so you're going to be going through the notebook, right? A rundown of the notebook, and then that will be helping them for the assignment as well, I believe, correct?
I would be going through.
Okay. Would you rather complete that so that in case if somebody wants to leave a little bit earlier, something like that, so that they can have the work that they can do it during the week? And probably we can come back to you very shortly. I'm sorry. Yeah.
Fair. I'll just take off my screen and be vanished for a moment, and I'll be back. Yeah.
Sure. In the moment, and in the meantime, I've learned a word called jellyfish, and it's very interesting to share that with you. I know that we have like about over 50 participants in this session right now. I know that somebody has some interest and they wanted to ask this question. I'm not denying that, but whether that could be an interest to everyone in the session. That's the kind of term that we can use, something called jellyfish, that we can take it this offline. We don't have to discuss it in this particular forum and things like that. So I learned it. It's a very interesting thing. I would like to share this information. This is from Harvard, actually. And probably you can all use this word going forward in this SLM bootcamp. And so I'm not a strict officer, by the way. Just want to be making sure that how do we make use of the time effectively for all the participants. I know that you are taking away time from your family. This is very important for you. At the same time that you're also spending your valuable time. So I want to make sure that the time spent is well utilized. Okay. Also, any questions from the assignments that was given to you last week? I think that was kind of just a kind of a configuration. You just have to utilize it. It's a kind of a self. Experimental kind of thing like that. So any questions on that? I believe the discussion forum is open in Discord. You can definitely put a little bit of a brainstorming there. But if you have any questions, you can reach out to us. And again, I'm going to say the same thing. So the reason that we are going through deep in the topics is that we want you to let you know what is under the hood, right? It's not necessary that you need to know each and everything block by block in the transformer architecture. A lot of these things are now abstracted, available to you, but it is better that if you know that how this is all happening under the hood, but it's not that mandatory that you have to learn each and everything by heart, right? So it's not required that. So I just wanted to leave that because a lot of this people, participating in this boot camp, you don't have to know the 9 yards of the process there. So it's good to learn, but it's not that mandatory that. But if you are looking for SLM building for your use cases or things like that, so you have some of this abstracted code, and then you can just take it and then work on your data. That we are going to be covering it up tomorrow. It's a very important session. But this is some of these things, very technical, deep technical. You don't need to know everything there. So I just wanted to leave that. So don't feel bad that if you're not able to understand every block in this architecture, that's totally fine. Hope I'm making that right statement, Mohit. I know that you took a lot of effort in explaining that.
Yeah, that's fair. I mean, I was working since the last week to pull up all of this, and for me to pull it off in a week was very hard. So I mean, for you guys landing it in the first go is, I totally sympathize with all of you. But yeah, I mean, you'll enjoy it and you'll love it if you just take a look at during the notebooks. So you'll get deeper understanding of it. So yeah. Yeah, so let's give you a run through that how you should be approaching this notebook and the assignment. I mean, I don't want to call it an assignment because it is fairly straightforward. I have given up the equations there and there, and you guys would just have to understand and factorize the code in the notebook, right? And none of it would require any GPU or anything. You can run it on your local computer as well. So because it's fairly math, right? So we do not want GPU for that. So yeah, this would be the understanding that what topics we are going to be covering, and this is the housekeeping code. You do not want to code anything over here. This is the decoder block which you learned already in the GPT-2 architecture, right? We are taking the understanding of it, and it would give you a diagram of it. And the math, again, the equation that how it should be running, the GPT-2, how GPT-2 architecture runs, right? Now we get into the today's topic, that is the normalization. The first thing that we saw, the pre-norm and the post-norm thing, right? So this is the code for pre-norm thing. I do not want you to code anything in this block. It's fairly straightforward. It would give you a matplotlib plot, and yeah, it would fairly give you a matplotlib plot, and you would be understanding it through visualization only. The next thing is, this is the math and the equation of the pre-norm and the post-norm, and this is the derived thing exactly over here of layer norm that we discussed, right? That how we progress from layer norm to RMS norm. And yeah, this is the same math. Again, over here, I want you to do hands-on and get your hands dirty over here to write the code for RMS norm. That is, I simply want you to replicate this equation in the to do format over here. Compute the mean squared of it. It's fairly commented over here, and you guys would just need to understand and intuitionalize this equation and convert it into code over here. Because I take this method whenever I'm learning a concept. I take a look at the equation and I try to write it down in some form. And by writing it down, we can write a code, or we can handwrite the note of it. So over here we can write a code, and you will get a pretty good image out of it, and you'll just feel good about it that yeah, I learned it intuitively, and it's a fairly interesting topic. Yeah, so this is also the output of it, and we are still in the RMS norm topic. Now let's move on to the rotational positional embedding rope thing. And this would also give you the first architecture picture that how rope works. And this is the math of it. And this is where I want you to again get your heads dirty. I wanted to apply this equation in the form of code, right? And wherever there's to do written over here, it's where you guys should write and write over your intuition in the form of code. That is, initialize the code and define a variable, and then try to convert this equation in the structure format. And yeah, again, let's get into the GQA session. Same thing, you'll get fairly good understanding of the picture, and then we do the same thing. We have a pattern over here that we try to convert the equation into the code, right? Again, checkpoint 3, and then now we get into the Swiss glue uh, activation unit, and first the image and the to do code. And again with the MoE. So MoE over here, you'll get an image, and you try to route the token as well over here. You are given certain amount of equation over here. You have to flat it out. You have to renormalize it, and we have to add weighting on it, that how it should not bias into one feed forward network, and it should go again. It should uh, give weightage to all of the layers. Yeah, that's pretty much it about MoE. And then at last, the thing which we did for GPT-2 in the very start, we would do the same thing for the improvised upgrades thing. So this is the code for that, and you'll be able to understand that how it changed, that the how layer norm changed and how the whole wiring and things changed, right? So yeah, that is the pretty brief run through of the uh, code. And yeah, I do not want you guys to spend GPU hours on this and anything, but I just want you all of you guys to have fairly good intuition of how the equations work, because this was majorly math, and I tried to land it very easily on you guys, because and I try to add more intuitions to it as well. But if you guys still have queries, and if you guys still want to understand it briefly, feel free to uh, brainstorm with me on Discord, or else anybody from the TAs and my friends would be happy to help you out in this as well. Yeah, with that, this is Mohit. I really love teaching this in the evening, and that's a good wrap from my side. And yeah, Tirth, you had a question. I be happy to take over that if time
Yeah,
permits. Yeah,
so
Venkat,
Yeah,
go ahead.
absolutely. Over to you, Turth. But also, there is a person. I'm sorry, again, I'm putting there. So, Annapurna, I think. So, if you want to come out of your mute and ask this question, so are you saying that please mention what you need to know and not to build SLM? How do I read this question? Because this is all about SLM building, right? Do you want to come out of mute and briefly explain the question a little bit more? Okay, so probably like I'll just give a brief. Okay, I think maybe we'll go with Tirth, and then we can come back to you, Annapurna. Yeah, please go ahead, Tirth.
yeah. So for the MOE architecture, like the analogy that you used, right? That one expert would be for let's say grammar, and another would be for another task. But actually, we are passing the same tokens to all the experts, right? So how are we making sure that one expert is actually learning a single task? Like that was my question. So it's
Through
like, is it a topic
I get it.
expert or like?
No, it's not like that. So I was very cautious to not give you this intuition, any of you guys, that we are doing it. I mean, no, we are not doing it. It's an black box autoregressive process, right? So when I mean, you should understand the whole hierarchy. We have discussed swish glue just before that, right? And by that, we used gated over there, gated attention, right? So we try to give some amount of tokens to certain feed forward layers, and and by doing that, it is learning something or the other, right? That is, if we are giving it the and vowels and things like that, grammar like that, it would be getting expert in that. But if we are giving it and if we are giving it other task, it would be getting expert in that. But we are not choosing the data for that. But yeah, we are not choosing it. It's an autoregressive process. We are just chunking the FFN layers into multiple layers. Yeah,
So we are
that was
not
the answer.
even training that router. It's
We are
for
effectively training
particular.
just the router to do this. We are just effectively training the router to do this. We are not at all training the FFN. FFN is just chunked part. If this would be an FFN layer in total, we are just chunking it off, and we are adding a router in front of the FFN, and it would be deciding which token to go where. So this happens in inference layer. But if you take it at pre-training layer, the router is also as unaware as we, right? So it all runs in the pre-training, and then when we do inference, the router is very smart enough that to route it in which FFN layer. That is how MOE works.
Perfect. Annapurna, are you ready?
Yeah, sir. Can you hear me?
Yeah, We can hear you.
Yeah, so I was asking that we are also covering the theory and the practical hands-on that in together. So, like for st in Scratch, if you are starting with that SLM, so from where we can start it? Like initially, where from
Perfect.
where we can start?
Perfect. That's a very right question. I should say that because I think I've given the brief a little bit in the initial, the first day lecture. So let me run over it again, right? So, yeah, this is the purpose of this SLM bootcamp is that, we want everyone to build an SLM from scratch. And so we don't just wanted to get into the building of SLM, we wanted to understand the intuition around it, right? So those were the day one, day two, and tomorrow also we are going to be covering a little bit on that actually. And so in order to build an SLM, there's 8 steps in the process there, right? You would have seen this in the day one session, like starting from data, then to the inference, right? And then evaluation and then inference. But right now, what we would like you to do is that make sure that what is that use case that you're going to work on? Do you have a data set? Is it pre-processed, cleaned, and things like that? That we are going to cover it in tomorrow's session about the data strategy. How much of data that you need? So all this kind of questions. Tomorrow's sessions will answer all these questions there. And once we are done with it, so now, right now, all you need to have is that what is that use case that you're going to build an SLM on, right? If it's going to be a task specific, domain specific, do you have enough data? Are you planning to generate that synthetically? That's something that you can think about it. And tomorrow's session will give you much more clarity in terms of a data, what kind of data that you want to do it, or that you want to select for your use case. And then it's going to be a 2-part session tomorrow. The first part is going to be all about data strategy. The second part is all about data engineering. So if you have a data with a lot of noise, how do you cleanse it, pre-process it to make it model, training ready data, right? That's something that we will cover it in tomorrow's session. And after that session, as part of the capstone project, you will start working towards your data, the data engineering part of it. Make sure that then you will see that you'll get at the vocabulary, the tokens. So you will be ready for that model training. Then on the next step would be like selecting the model architecture. Then you will go for the model training process. And then you have a post training. And then you will do an evaluation there. And then finally, you'll do an inference either through I think Dr. Deepak was asking, saying that can we go ahead and build a chatbot or an application? You can definitely do that. That's probably would be a stretch goal. But now you will have all the steps from data through inference. Does that answer your question?
Yeah, so it's pretty clear. Thank you so much.
Yeah, no problem. That's a right question. And because we don't want to jump right into the SLM building, otherwise you won't know what's what, right? And things like that, because that's what we wanted to go from the beginner friendly to the advanced level, because we wanted to make sure that we are catering to the needs of all participants in this boot camp. So we just don't want to jump into the building right now. And the capstone project is scheduled in such a way that, you will have step-by-step guidance, making sure that we want everyone to build SLM at the end of this bootcamp. That's our goal. So we will guide you there. And if you have any questions, please feel free to reach out to us through Discord by any other channel, and we will support you throughout the journey. Okay. But that's a great question. Thank you so much for asking it once again. And if you still have any questions related to that, please feel free to reach out to us. Okay. Any other questions?
Just one question. I mean, so let's say Chinese models versus US models. I mean, if we want to pit it against, I mean, they're coming up with such brilliant models. Like say, closed models comes in another 3 months or 4 months, they release one which actually challenges this, right? They may not have the great kind of resource what US might have. Say, for example, they're denied on the B300, a GB300 of the class of GPUs. Are they only focusing on the algorithm and math aspect of it, or also they're focusing on the computing saving every cycle of it, every memory of it? Have they gone to that extent? We used to do that like in our old days, right? So DSP programming using this DSP architectures where every cycle optimization, every multiplication and MAC units of it, we used to optimize to that level. Uh, I mean, trade-off wise, I mean, where do they land? I mean, how are they able to come up with such kind of models with less computing resource at their end?
Perfect.
So
But that's a very good question. Again, that's going to be a own debate. I would say that, we can ask the debate between the Chinese models and the US models. And there's a good session that I wanted to share this deck actually that talks very good about, the question that you're asking. Let me just to check out that if there is a graphic available so that I can just pass it on to this team as well. Just a second. I will forward it to you if I'm not finding it in the next 30 seconds. Otherwise, okay, I'll share it out later on. But that's a great question. Also on the consumer landscape and the enterprise landscape, right? So there are a lot of threads within that question that you asked. It's not just right one answer that we can say that. I know that there are compute efficient. They are working a lot on that in terms of a DeepSeek. Like they come up with a lot of versions now. DeepSeek 4 probably is the latest one, if I'm not wrong. Um, in terms of where they are hitting the road, right, in terms of the consumer market or the enterprise landscape. And in the US also, earlier, enterprises are not getting into that the models, but now we see that because we take that model, it's an open source, and then you can put it into your perimeter, and you can grant access to your resources there. So no more in terms of challenges in terms of a governance and things like that. In terms of I would say that in terms of the compute efficient things like that, what is that they are using in terms of the technicalities to say that how can they build the model with such a limited resource? Is that you're nailing down to that question?
Yeah, precisely. Yeah.
Yeah. Probably I'll take it as a homework for myself to understand. I know that there's different architectures available there, but I can answer to you a little bit later once I found that slide also. But this is more predominantly now that's been more in the competing landscape these days. And again, if you go deeper into that in terms of a consumer and the enterprise landscape also, it is definitely a point to be taken, and we need to think through to see that how can we make it the efficient models, right? So I'll come back to you on this for sure.
Thank you, sir.
Any other questions?
Yeah, I had a question about the mixture of experts. So, the loss term that you showed us that prevents the router from like biasing all the tokens over to one head. How do you weight that with the main training objective, like the cross entropy loss? I'm assuming you can't just like add it in directly, right?
no, we can. I mean, in router, it's a training loss for a router, so to say, and not for the whole transformer.
Okay.
Yeah, I have uploaded the slide. I do not want to share that again. But if you take a precise look at the MOE architecture, we have split the FFN layers into multiple layers, and there's a router in front of it, right? Before it, my bad. And it is a loss term for router and not the transformer layer. So by auxiliary mean, I mean auxiliary loss. I mean loss function for router, and the cross entropy is for the whole transformer architecture.
I see. So the cross entropy gradients are used for like most of the weights, and the routing loss is used just for the router's parameters. Is that
Yeah,
how it
yeah,
works? Got it.
yeah, and that's why we call it as an auxiliary loss along with cross entropy. Yeah, so the
Okay.
regime is different for both of them.
All right, got it. Thank you.
Yeah, okay.
Okay, I think we're at the top of the hour. Thanks everyone for joining in, and as I mentioned that tomorrow that we are going to deal about the data strategy and the data engineering part. It's very important, and that's going to be your first step in the process in terms of SLM building also. So don't miss the session, and yeah, we'll be communicating anything through the Discord if there is anything that we want to let you know about it. But otherwise, I think Mohit has given you something. If you wanted to take a look into it today, or probably you have entire 5 days to deal with it. So there are no other questions. Thank you very much for your time, and have a great
Thanks, guys.
Thank you. Thank
Yeah.
you.
Bye. Have a good evening.
Thank you.
Thank you.